fields. Electric field, a field of force surrounding a charged particle associated with static electric charges, is called as electrostatic field. Distribution of static charges produces an electrostatic field. Electrostatics is an interesting subject and it finds applications in diverse areas. Coulomb's law. Coulomb's law states that the force F between 2-point charges Q1 and Q2 is, along the line joining them, directly proportional to the product Q1 Q2 of the charges, inversely proportional to the square of the distance r between them, expressed mathematically. Q, charge in coulombs, r, distance between the charges, where k is the proportionality constant. Q1 and Q2 are in coulombs, c, the distance r is in meters, m, and the force F is in newtons, n, so that where epsilon naught is equal to 8.854 into 10 to the power minus 12 farads per meter is called the permittivity of free space. Consider 2-point charges Q1 and Q2 located at points having position vectors r1 and r2. The force exerted on Q2 due to Q1 is represented by F12 and is given by following are to be noted. The force F21 on Q1 due to Q2 is given by F21 is equal to mod F12 AR12 is equal to mod F12 minus AR12. Unlike charges attract each other and like charges repel each other. Distance r between the charged bodies Q1 and Q2 should always be large compared with the linear dimensions of the bodies, that is Q1 and Q2 must be point charges. Q1 and Q2 must be static at rest. Signs of Q1 and Q2 must be considered for sure. The more than 2-point charges, say n charges Q1, Q2 till Qn, located at points with position vectors r1, r2 till rn respectively. The resultant force on a charge Q located at point r represented by F is the vectorial sum of all the forces exerted on Q by each of the charges Q1, Q2 till Qn. Hence, electric field intensity or EFI. The electric field intensity can be described as a vector field through the charge Q. E is the force per unit charge when placed in the electric field. The electric field intensity is in the direction of the force F and is measured in newtons per coulomb or volts per meter. The electric field intensity at point R due to a point charge located at R' can be given by, for n point charges Q1, Q2 till Qn located respectively at points with position vectors r1, r2 till rn, the electric field intensity at point R is obtained from electric field intensity due to continuous charge distributions. Line, surface and volume charge density are denoted by rho L coulomb per meter, rho S coulomb per meter square and rho V coulomb per meter cube respectively. If the total charge is fine, then the volume is obtained as Q is equal to integral volume rho V dV. The charge dQ and the total charge Q due to these distributions are the EFI produced due to line, Surface and volume charge distributions is given by the sum of the field that are contributed by the numerous point charges making the charge distributions. By replacing Q with charge elements rho L dl, rho S ds and rho V dV and integrating, we have electric field intensity due to line charge. Line charge. Consider a line charge having uniform charge density represented by rho L stretching between A and B along the z-axis. The charge element dq in relation with the element dl is equal to dz is given by dq is equal to rho L dl is equal to rho L dz. The net charge q is given by the EFI or E at an arbitrary point P, X, Y, Z is determined by using the following formula. The field is evaluated at a point called field point which is represented by X dash, Y dash, Z dash. Source point is denoted by X dash, Y dash, Z dash. From the image, substituting all into this equation, we get, to evaluate this, it is convenient that we define alpha, alpha 1 and alpha 2. Thus, for a finite line charge, as a special case for an infinite line charge, point B is at 0, 0, infinity and A at 0, 0, minus infinity, so that alpha 1 is equal to pi by 2 and alpha 2 is equal to minus pi by 2, the z component vanishes and electric field intensity due to surface charge. Surface charge. Consider an infinite sheet of charge in the xy plane with uniform charge density rho s associated with an elemental area ds, that is dq is equal to rho s ds. Hence total charge q is equal to integral rho s ds. The contribution of the E field at point P 0, 0 h by the elemental surface 1 is substituting the above equation in dE. Due to symmetry of charge distribution, for every element 1, there is a corresponding element 2 whose contribution along A rho cancels that of element 1. Thus, contributions to E rho add up to 0 so that E has only Z component. This is shown by mathematically replacing A rho with cos phi ax plus sin phi ay. Integration of cos phi or sin phi over 0 less than phi less than 2 pi gives 0. Work done in moving a point charge in an electrostatic field. Consider